solve, well, we have solved technically 29 problems so far, but we want to solve 2 more so that we get to 30 problems today. And so we will be able to finish 100 problems in a relatively shorter amount of time. If I have some holidays planned, then I'll be able to do more. But at the moment, it's probably 2 problems every time I log on. So yeah, there you go. So let's try to do 2 problems today, and let's see how things go. So let's start with problem 29. And problem 29, okay, so for problem 29, let's start a new Jupyter notebook, and we will call this problem 29. That's problem 29. And let's copy the problem 29, and it is called distinct powers. So let's see what the problem is. Okay, so what is the problem? Consider all integer combinations of a to the power b. So that's a to the power b, like that, for these conditions. Wow, this is actually a unicorn. Okay, so I don't actually have to convert it into a problem. And if we have these functions, then you have, it's 2 to the power 2. So all of these things are supposed to have a power. Let me see if this works. If this works, that will be perfect. Oh, perfect. Okay, 2 to the power of 2, 2 to the power of 3 is 8, 2 to the power of 4 is 16, 2 to the power of 5 is 32, and so on. And if we continue this, we will see that there's 3 to the power of 2, 3 to the power 3, 3 to the power 4, and so on. So we have a bunch of powers. And what is the task? The task, let me just finish this, give me a couple of seconds. Yeah. So what is the task? If they are placed in numerical order, so okay, so we place them in numerical order with any repeats removed. Okay, so we have, for example, 16 over here and 16 over here. There are 2 of them. 2 to the power 4 is 16 and 4 to the power 2 is 16. If these things are removed, we get the following sequence of 15 distinct terms. So that's this. How many distinct terms are in the sequence generated by a to the power b, where a is between 2 and 100, both inclusive, and b is between 2 and 100, also both inclusive. So so how many distinct terms? That's the key. So if we are talking about how many distinct terms, I don't think we actually need to put them in numerical order. So we don't need to sort this. We just need to find the number. Okay, so we can actually loop through about 100 by 100 different items, but we have to then eliminate a number of things. And the other thing is, obviously, 100 to the power 100 is a fairly big sum. So we know Python can do arbitrary precision integers, but I don't think it is necessary over here. So let's see how we can tackle these 2 problems. let me take out my notebook, my iPad, and let's try to see how we can have a good representation of this. Okay, so if we have a to the power b, so we want a to the power b, so that's basically what we want. And in cases of, for example, 2 to the power 4 and 4 to the power 2, I am guessing that there is no need to represent this as 16 and this as 16. What we can do is we can still represent this as 2 to the power 4 as a tuple. Okay, 4 to the power 2, this can also be represented as a tuple, 4 to the 4 comma 2. But one thing we need to do is, let me see, this 4 can be represented as 2 to the power 2 to the power 2, and this would lead to 2 to the power 4, which gives back, and this can be represented as 2 comma 4, and we will get back the same same value. So instead of saying that we have to multiply or take the power and get 16, and over here take the power and 16, we can just keep it as this. So one of the things that we need to do is to break this a into its prime factors. So for example, let's say we have the number 10 or 18. We have the number 18, and 18 to the power n, the n doesn't matter. The reason I've chosen 18 is because it is 2 times 3 squared to the power n. So that's if we have a power n, then that's what it is going to be represented as. So 2 to the power n, so this can actually be represented as 2 to the power n multiplied by 3 squared to the power n. So excuse me, and this can be represented as 2 to the power n multiplied by 3 to the power 2 plus n, if I or is it 2 into n? I think it should be 2 into n. We can quickly check that. Okay, we can quickly check that. So let's say we have 3 to the power 2. Oh, that's not to the power, that is to the power 3 to the power 2 and to the power 3 is that, and 3 to the power 2 plus 3 is that, but 2 times 3 is 792. So we know that we have to multiply these two. Okay, so 3 to the power 2 times n is what we need to do. So that's the idea. If we have, for example, something like 18, then we have to then we can represent it as, let me I haven't actually put this. Yeah, so if we have something like 18 to the power n, we can represent it as 2 to the power n and 3 to the power 2n. So that is a representation of 18 to the power n in terms of its prime factors. So that's the idea. Okay. So let's try to so what are the things that we need to do to solve this problem? Number one, so a to the power b, we don't have to do anything. A goes from 2 to 100, okay, both inclusive, and we have to find prime factors of a. So this will be the prime factors we will have to represent as a list of tuples. So f1 and exponent 1, f2 exponent 2, f3 exponent 3, and then we update it so that, so this is the calculation of a. A is that a to the power b is going to be equal to we just multiply f1 exponent 1 times b, f2 exponent 2 times b, and so on. So that's the this, and then we just need to add it to the set of all things. So that's I believe the way we need to solve this problem. So first let's find the prime if we are given a prime factor something like 18, we need to figure out how to represent that number to begin with. Okay, so let's write a function, find prime factors. Okay, so before I create prime factors, I think I need to get a list of primes and all the way to 100. So I think this is something that we have done often enough that I can almost do it without thinking. So this is a list of primes, and we have a list of numbers range from 2 to 101. This is an iterator list. Okay, and we want to work with NumPy for these types of problems, and this will now be a NumPy array. Okay, and while length of nums is greater than 0, what we do is we will take the first element is nums 0, and we will append it to primes, the first element. Then we are going to update the number so that all multiples of it are no longer within it. So nums equals nums, and if nums percentage f is not equal to 0, then we keep that and we remove the rest. So if we do that, we look at nums and it's empty, and we look at primes. We see that we have a list of primes that goes from 2 all the way to 97. So 97 happens to be a prime. Length of that. So we have 27 primes. So now that we have a list of primes, the next step is to find the prime factors of A. So given a number, we now need a function that gets the prime factors of a given number n. Okay, for p in primes, okay, factors is an empty list for p in primes. Okay, if p is greater than n, we don't want to go all the way up to 25. If, for example, we are looking at 2 or 3, then we only want to have like a few of these things. Okay, 18, we only want to go up to between 2 and 3 and so on. So that's the idea. Beyond that, let's look at if the number n percentage prime p is 0, okay, then it's not equal to 0, we just continue. So these are things that we keep on doing. And now in the situation where p is actually divisible by n, we have to get into a while loop and create the factors. So n times is a variable that I will update. The number of times p goes by the number of times p goes into that prime number p goes into n. Okay, so while true, at some point p will no longer go into this. I want to first append I want to see p is not p, n is divided by p. So while n which p is 0. Okay, that's another way of writing it, but yeah. While it's divisible, divided n and then when this is done, we want to append this tuple, which is the prime p, and the n times, and we want to return return factors like that. Okay, so So if we want to find the prime factors of 2, it should just give that. If we want the prime factors of 18, it should give 2 and 1 and 3 and 2, as we had found over here. It should be 2 and 1 and 3 and 2. Okay, so that's the prime factors. What about 4 to the power 5? 4 to the power 5. The prime factors are 2, 10. Okay, that makes sense. It automatically does all the things that I need to do. And then when we raise it to the power b, I need to go through and just multiply these, the second values, by b. Okay, so that's the idea. So let's go. So we have a start and b start equals 2 and 5, 2 and 5. Oh, sorry, a start and b start is 2 and 2, and a stop and b stop, a stop and b stop is, at the moment we will do all the way up till 5 and 5, 5 and 5. Okay, and we want to loop over these things. For a in range a start to a stop plus 1, because that is included. For b in range, what is that called, a start to, oh sorry, b start to b stop, b stop. Okay, let's just print a and b, print a and b for the moment. So let's print a, something like that. So that's a and that's b, and we also want to v equals, that's the value, prime factors of, oh, I just need to calculate this once, right? Prime factors of a, yeah, a, like that. So let's look at and v's. v1 equals for, so this is going to be an array for m1 and m2 in, so it's going to be a list of tuples. So we are m1 is going to be the prime factor, m2 is going to be how many times it goes. In v, we are going to have the value m1 and m2 times b, and let's print v1. Okay, so for 2 you have 2 to the power 2, 2 to the power 3, 2 to the power 4. For 3 you have 3 to the power 2, 3, 4. 4 you have 2 to the power 4, which already appears over here. 2 to the power 6, 2 to the power 8. Okay. We want to make sure that we have, let's say we go all the way up to 10 to see that this is working fine. 2 and a stop is 10, like that. So over here 6, we see it's 2 and 3, right? And 10 square, we have 2 and 5, 10 cube 2 and 3, and 10 to the power 4, 2 and 4. 8, for example, we see 2 and 6, which should already be 4 to the power 3, and 8 to the power 2 should be the same thing. Okay, so it looks like we have all the things that we need to find the solution. Okay, so if we go back to 5 like that, okay, and let's put it over here. Let's put it in the same cell so it'll be evaluated at the same time. Okay, and all numbers equals an empty set. Okay, and over here we want to say all numbers dot update v1, right? So that's a new thing, and let's print all numbers. So wait, that is not correct. That's not what we want. We want this to be a tuple. V1. Oh, not like that. Like that. So we are converting this into a tuple. And hashable type list. V1, we want to convert this into a tuple, like right over here. Okay. Oh, we don't see it because we only went up to 5. So let's go up to 10. 10. Okay, there you are. Did we have to do this? Did we have to actually do the tuple and everything? This is something that was necessary. Okay. And do we have to do this? We also have to do this because it is 2 4 3 4 2 4 5 4. Okay, we still have to do it. So the solution to the problem requires us to count these things, right? We don't care about any of this stuff. We just need to find the length of these numbers, and that equals let's look at 5 and 5. And do we have 11? We have 15 distinct terms. So obviously something is not correct. Oh, b stop plus 1. We need to do this plus 1. Okay. So we have the right number of counts for when it goes to 5 and 5. What we want to do is go all the way to 100, 100. Right? 100 and 100. And we get this number over here. Let's check if this is correct. Paste. Okay. So this was fairly easy, I would say. Okay, so let's do one more. So if we refresh this, we will have seen that we have 29. We have done problem 29. Let's do one more problem and then we will call it a day. Okay. Okay, so power of their digits. Okay, interesting. Find the sum of all numbers that can be. Okay, so let's start a new notebook over here, and I don't think I need this notebook, so I will shut this down. Okay, let's create a new notebook called problem 30 like that, and problem 30. This is called digit fifth powers, like that. Copy everything, paste it. There should be $. Okay, and these are all powers. Power, yeah, I should be able to do. There you go. Power. Yeah. Let's mess this up. What the hell is happening? Oh, now I understand. I have to do this. And also like this. And that. And if I do this and do that and do that, I wish I was using Sublime Text. Never mind. Okay, so let's read the problem. Surprisingly, there are only 3 numbers that can be written as sum of fourth powers of their digits. Okay, they are these are the numbers. The sum of these numbers are that. Okay, find the sum of all numbers that can be written as the sum of the fifth power of their digits. Okay, so the power is p is 4. Okay, and we have to get a sense of how big the number should be. So for example, let's say 9 to the power 4 is that. So it 9 to the power 4 is that. So let's say we are averaging out between 0 and 9. So approximately 5 to the power 4 is that. And if I have 4 of this, we will have that. Okay, so it will, and 9 to the power of 4 is that. How about a power of 5? 9 to the power of 5 will be 6 digits. 1 2 3 4 6. It's 6 digits. So we need values that are worth 6 digits. Oh, okay. So if we have 1, or not 4, just that is 1 2 3 5. This is 5 digits. So the maximum, let's say 4 into that, is 6 digits. But I can't have that. So what's the average? 5. If I have 5 of these, it's 1 2 3 4 5 digits. If I have 5 digits, 1 2 3 4 5, still 5 digits. So I can have so I'm thinking that it is the digits will be in the fifth range. So there should be about 5 digits within them. But we can check between, yeah, we cannot have all 9s. If we have all 9s, then obviously it won't be 5 digits anymore. Okay, let's try one thing. For I in range 1 to 10, okay, print. So if there are 4 ones, I to the power 5 times 4. 4 of these. So 1 2 3 4 5 6. If it's 9, it's 6 digits. And if it's 5 digits, one, two, three, four, 5. 1 2 3 4 5. This is 4. What about 6? 6 and 7. 7. So let's actually print it so that it's an F string, and I will be able to so they're all very similar. Okay, so I think we have found the upper bound. So even if we have, so this is 9, right? I just want to emphasize. So let's understand what we did over here. Okay. So basically what we did was we saw that if the digits, these digits, they are all 9s, okay, and they are raised to the 5th power like that. Then what's going to happen is that if they're all 9s, they will give 1, 2, 3, 4, 5, 6. 6. Oh, I think I have made a mistake. Oh, boo boo. 5. Uh, so it should be to the power 5. Oh, yeah, so that's correct. So if we have anything raised to the power 5 and we have 7 digits, okay, so that's 7 digits. Then it 9 to the power 5, a 7-digit number will only have 6 digits, 1, 2, 3, 4, 5, 6. So we cannot have a number like that which is 99999, and we can raise it to the power, and we will end up with 7 digits. So we are left with 6 digits, anywhere between 4 and 6 digits. That's the range. It's okay. Are there numbers in 4 digits that can add up to the original digit? Most probably yes. Most probably yes. So we have to check. We have to most probably check 4-digit numbers and 5-digit numbers and 6-digit numbers. Those are the numbers we have to check. So let's check those numbers for n in range. We can go all the way up to 6 digits. 1, 2, 3, 4, 5, 6. Okay, we can go all the way up to that, and we will see whether now p equals 4. Okay, so we will later make p equal something else, the power that we are interested in. We'll make it 5 later, but we want to make sure that when p is 4, we are actually able to get these 4 numbers. Okay, so we take n, we take the string of n, and then we take the integers of it each, and for I in that, I to the power of in this case p equals 4, and then we take n1 is the sum of that. So we convert n into a string. So let me try and explain what's happening over here. If you put n equals, let's say 25, 25, you will see that it's 2 to the power 4 in this case, because p is 4, and 5 to the power 4. Okay, and then when you sum it up, it's going to be the sum, and we want to see if n is equal to n1. I don't know if there can be print n. Okay, and we don't care about 0 and 1, but we have the numbers 163, 828 and 9474. Those are, so we start with 2, and if we do that, we will have these 3 numbers, right? And we want to look at all values equals that, and we will say values dot append n, like that, and we want to find the sum of n, sum of all values, and the sum of all values is that 19316. So it works for p equals 4. Now we want p equals 5. Okay, there are actually several numbers like over here where to the 5th power is equal to interesting. Let's check. So if we have that, 0 is the reason why it's only four values. Okay, so this is the answer, which for some reason it keeps on giving me something like this. Let's paste this and see whether this works. Okay, so we have solved all the problems till problem 30 and one more. So we'll stop over here and we will continue next time. Thank you for watching, and in case you like content like this, please remember to like and subscribe, and I will see you next time. Bye bye.